Next, let us discuss how in-band signaling system would look like. Sometimes in-band signaling is also called as voice frequency signaling, VF signaling. So voice frequency signaling, because here we will be dealing with addition of control signals into our speech band. So that's why, or into our voice band, that's why we call this in-band signaling also as voice frequency signaling. In telecommunications, in-band signaling is about sending control information or control signal within the same band or channel used for data such as voice. So whatever the channel we are using from 300 Hz to 3.4 kHz for speech band. So within that same band we are able to send our control information or control signal with a particular frequency. So that is what in-band signaling is about. So whatever the channel we are using in order to send voice, so in the same channel we are inserting this control information. That is what in-band signaling is. So the system that transmit control signals within the baseband of FDM system or FDM carrier system are known as in-band signaling systems or voice frequency signaling systems. So this in-band signaling system is having two important advantages. The first advantage is this in-band signaling system is independent of the transmission system what we are using. So whether we are using FDM transmission system or TDM transmission system, so this in-band signaling system operates in both transmission systems. That is one big advantage of in-band signaling system. Not only that, so this in-band signaling system also functions well inside a circuit which supports or which allows speech transmission. So whichever the circuit that transmits speech, so in all those circuits we can make use of this in-band signaling system for adding control signal. Please note that control signals are very much required to operate the exchange or to operate the switching equipments. This is how an in-band signaling system would look like. On two exchanges we will be having switching equipment as well as signaling terminal. Similarly on the other side also we will be having switching equipment and the signaling terminal also. So please note, so this in-band signaling system includes whatever the components that are used on one side as well as on the other side along with intermediate part. We know switching equipment gives the speech signal along with the carrier, and for this we need to add our control signal. So generally we are using some control signal. Of course the frequency of this control signal will be inside this speech band, that is from 300 Hz to 3.4 kHz. So once we add that control signal to our carrier as well as speech signal, please note we are dealing with FDM carrier system. So the combined signal will be transferred from one exchange to another exchange via this 4-wire circuit. Please note we are not writing this or we are not mentioning this as 4-wire FDM circuit, because we know this in-band signaling system is operating both in FDM system as well as TDM systems. That's why by excluding FDM we are writing just as 4-wire circuit. Whatever we have shown from here to this end we call it as outband signaling terminal. Similarly whatever we have shown from this end to this switching equipment, in between we will be dealing with incoming signal terminal, because this is outgoing and the signal is incoming at the receiving end. That's why the name incoming signaling terminal. Please note we are using line split at transmitter end, as well as we are using line split at the receiver end also. So this line split is used in order to confine this carry control signal, or sometimes this control signal is also called as tone signal. So in order to confine this tone signal into the concerned link, into the concerned circuit, we are making use of this line split. So with the help of these line split, we are able to add this tone signal or control signal into our system. Similarly, with the help of this line split, we are able to remove the control signal. We are able to remove the control signal, and we will be able to forward only carrier signal and speech signal to our switching equipment and then to our customer, end user. Similarly, at this end user will send carrier and speech signal into our switching equipment. Via the switching equipment, it will be forwarded to signaling system. Please note, at the receiving end, we are using VF receiver. This voice frequency receiver is basically used for extracting the control signal, or in order to provide DC signal to our switching equipment. In order to provide DC signal to our switching equipment, we will be using this voice frequency receiver. Basically, this voice frequency receiver will extract this control signal from the speech signal as well as along with the carrier. So extraction of control signal or tone signal will be done with the help of this VF receiver, and of course this VF receiver will give DC signal to switching equipment with the help of E-lead. Please note, in between this VF receiver and switching equipment, we are using unity gain buffer amplifier. This unity gain buffer amplifier prevents any transient signals being received by this VF receiver. So once the switching equipment is operating, in case of Stroger exchange, where we basically deal with electromechanical switching equipments. When electromechanical switching equipments are operated, sudden variation in voltage as well as current are observed. So those variations, sudden variations, sometimes we call it as transient. So those transients must not reach this VF receiver. If they are reaching VF receiver, then the VF receiver may give some DC signal with respect to the operation of this switching equipment. Such things should be avoided. Only this VF receiver should provide DC signal to switching equipment if and only if it receives the control signal. So the separation of VF receiver and the switching equipments, that is electromechanical switching equipments, will be taken care with the help of unity gain buffer amplifier. Please note, in this case, that is in band signaling system, we are using voice frequency control signals. So we are using voice frequency control signals, and there is possibility of signal imitation. So signal imitation, we know the speech signal, whatever we are sending from the transmitter end, may produce the frequency which is same as that of the control signal frequency or tone signal frequency. So in such case, the receiver do not understand whether it is control signal or a speech signal. So in such case, the receiver may operate wrongly or incorrectly. So we call such thing as signal imitation. So that is, the receiver may operate because the control signal frequency is present in our transmitted speech. So whatever we are transmitting our speech signal, within this speech signal only we may produce a frequency similar to that of a control signal frequency. In such case, the receiver may operate, whether the receiver may understand or the receiver may end the call, like that. Such things happens. So that is what signal imitation is. And of course we need to minimize the signal imitation, or the probability of occurrence of the signal imitation must be reduced with suitable design. And of course the signal imitation is an undesirable characteristic produced by the in-band signaling system. So what we do is, let us consider one example showing signal imitation. So it would clear down, or the receiver may clear down a connection before the user have finished their conversation. So once the receiver has received a speech signal with a frequency similar to that of control signal, the receiver may understand this is a clear signal and the receiver may close the connection or remove the connection before the end users have finished their conversation. So that is one drawback of in-band signaling or signal imitation that is occurring inside our in-band signaling system. Because we are making control signal to be there inside this speech band, and there are probability of speech signal of frequency same as that of the control signal. In such case, signal imitation may result in some problems. So in order to reduce the signal imitation, following measures are taken. So the first measure what we are taking is the control signal frequency is chosen at which the energy is in speech is low, that is above 2 kilohertz. So generally above 2 kilohertz the speech signal amplitude level will be somewhat lesser, or the energy of the speech signal will be lesser in that particular band or above this 2 kilohertz. That is, we know within 300 hertz to 3.4 kilohertz speech can reside, but generally above 2 kilohertz speech signals are less in number, or I can say the energy of the speech signal will be low. In that range we will be making use of control signal frequency to operate. So generally we select control signal with a particular frequency above 2 kilohertz. Generally what we do was, generally we select 2.28 kilohertz or 2280 hertz is used in UK, and 2.6 kilohertz or 2600 hertz in North America is used, which is for above 2 kilohertz. And within this are the property of having speech signal with the frequency of 2600 hertz with good amount of amplitude level is very less. That's why we are using control signal to be operating in this frequency band or within above 2 kilohertz. By using control signal above 2 kilohertz, we were able to minimize the signal imitation. And the second measure taken is the duration of the control signals are made longer than the period for which the speech frequency is likely to persist in speech. So generally the control signals are made to be there inside our system greater than 50 milliseconds. So of that particular frequency, please note that control signal whatever we are dealing with, it is of only one frequency, and if that signal is present in our system, that is signaling system, for time duration greater than 50 milliseconds, then the signaling system will understand this is a control signal or a tone signal. And we know generally when we are dealing with speech signal, we don't have that particular frequency for longer duration. When we are dealing with speech signal, so generally the frequency of the signal will continuously varies from one frequency to another frequency. So the probability of finding signal imitation will be less if we consider a control signal of particular higher frequency, of course greater than 2 kilohertz, and the duration of that particular frequency control signal is greater than 50 milliseconds. Generally the speech signal will not produce a particular frequency greater than 50 milliseconds. That's why we will make use of control signal to be operating at a frequency greater than 2 kilohertz, and the time duration of that particular control signal should be greater than 50 milliseconds. Otherwise if it is smaller, then the switching equipment may understand this is a control signal, and we know speech signals may produce this particular frequency, that is control signal frequency, for shorter duration, that is less than 50 millisecond. For shorter duration, there are probability of having speech signal of this particular frequency, that is control signal frequency. So that results in signal imitation. So in order to reduce the signal imitation, we are making the control signal duration or time period to be greater than 50 millisecond. The third measure taken to avoid signal imitation is, so we make sure that if speech signal is producing, let us say 2.6 kilohertz signal, so along with 2.6 kilohertz signal there will exist adjacent frequencies also. So it is present, or it is observed that adjacent frequencies are also present in case of speech signal. If I am speaking 2.6 kilohertz or 2600 hertz signal which is produced by speech signal, so there are more chances of having 2.55 kilohertz signal in speech as well as 2.65 kilohertz signal in speech. So that is what the probability of finding different adjacent frequencies in speech signal. But when we are dealing with control signal, we know control signal will be of particular frequency. We will be using exact 2.6 kilohertz control signal, and this will not be having any adjacent signal frequencies. It will be fixed frequency. Control signal will be a fixed frequency, whereas speech signal will be a variable, so its frequency will vary. Of course, we will find adjacent frequency in speech signal. So that fact is being utilized to understand whether it is control signal or a speech signal, or in order to minimize signal imitation. So with respect to this third measure, so let us consider one figure which gives the block schematic diagram of voice frequency receiver. So this is what the block schematic diagram of voice frequency receiver. We have already used VF receiver at the receiving end. So as you can see here, we have used VF receiver at the receiving end of our exchange, that is incoming signaling terminal. Inside our signaling system, we have make use of VF receiver. So please note that whatever we have used systems for one direction, similar type of systems will be used for opposite direction. So that is what the thing is. So coming to VF receiver operation, in order to minimize signal imitation, we will be having speech channel going to switching equipment. So as you can see here, we'll be having speech channel going to the switching equipment and then to the end user. So speech signal must be forwarded, and we have to identify, this VF receiver has to identify the control signal or tone signal. So what we do is, we will give this signal, whatever the signal the receiving exchange is receiving. So please note that the signal is having carrier signal, the signal is having the speech signal, and the signal is having the control signal also. Let us say this is the control signal, and this is what the carrier signal is, and this is what the speech signal is. So we know in order to carry the speech signal, we require carrier signal. That is what the modulation is about. We know the need for modulation. So before we give this signal, that is combination of carrier, speech and control signal, to VF receiver, that is voice frequency receiver, we will amplify the signal and then give that signal to two types of circuits. First type is signal circuit and the other type is guard circuit. So this VF circuit is constructed with the help of two circuits, signal circuit and guard circuit. The signal circuit will be having a band pass filter and then a rectifier. Similarly, the guard circuit is also having a band stop filter. This is a band stop filter, whereas this is a band pass filter. A band stop filter and then a rectifier, and both are compared. So both signals, after this both signals are compared and output will be produced by the VF amplifier, and we know, sorry, VF receiver, and we know whatever the output that is produced by the VF receiver will be given to switching equipment, so in the form of E wire. So we know DC signal will be produced and that DC signal will be given to switching equipment. So whatever the VF receiver has produced DC signal in the form of E leads, so it is given to switching equipment. We know that. So we have discussed in outband signaling system also. This band pass filter will be passing only control signal frequencies while attenuating, while blocking carrier frequency as well as the speech signal frequency. So it will be passing only the control signals, and those signals will be rectified and the DC signal will be given for this comparator. Similarly, on the other hand, in the guard circuit, we will be using band stop filter. So this band stop filter will block only the control signal frequencies. So it will block only the control signal frequency while passes other signal frequency, that is carrier frequency as well as speech signal frequency, and then rectified and given to the comparator. Please note, whatever the diodes used in this rectifier are opposite, because whatever the signal we are giving here is a negative signal. Let us say this is a positive signal, and positive signal, this is positive with respect to the other terminal, and this positive is given here with respect to the negative voltage. Similarly, this positive is given here with respect to the negative. So it means that negative voltage is applied to this guard circuit. That's why we are using a rectifier with the opposite direction of diodes. And of course, in order to convert this negative voltage into a positive voltage for comparison, so we will multiply this negative voltage with negative sign, so that we will have a positive voltage. So it is clear that this side we are able to receive only control signal, and on this side we are able to receive only carrier as well as the speech signal. Now based on these two different signals, so the comparator has to perform, or it has to produce, whether to produce DC signal or to produce no signal. We know this VF receiver should detect the control signal. If control signal is coming here, then only this VF receiver should produce DC signal to switching equipment. Let us say the control signal is coming along with speech as well as carrier signal. Let us consider a scenario in which right now we are receiving only speech signal and carrier signal. Okay, let us say only speech and carrier signal is coming, and we know it will block speech and carrier signal because it will allow only control signal. So the output of this will be 0. And similarly, on the other hand, this is a band stop filter which will block only control signal. Right now we are not having any control signal, we are observing only speech signal along with carrier signal. So the speech signal and carrier signal will be passed, and if right now this is 0 and we are having some signal, rectified signal, if the guard circuit output is more than this signal circuit, output, in such case this comparator will produce some output. It will produce some output. It need not to be a DC signal, it will produce some output. If the output produced by this comparator is there, then the receiver will operate. So the voice frequency receiver will understand right now there is no control signal, and whatever the signal is there, the speech channel, through the speech channel only voice signals, speech signals are coming into our switching equipment. Similarly, if let us say control signal is also there along with carrier as well as speech signal. So that control signal will be passed by this rectifier or by this band pass filter, and in such case there exists signal circuit voltage. There exists some signal circuit voltage. So in such case, if there exists signal circuit voltage, in that case the comparator will not produce any output. The comparator will not produce any output. So if there is no output from the comparator, in that scenario the VF receiver will understand right now some control signal is coming into the system and it has to take certain action. The switching system has to take certain action. That is how the VF receiver operates inside our in-band signaling system. VF receiver operating inside our in-band signaling system. So in order to avoid our control signal interfering with the speech signal, so what we do is, generally voice frequency signals must not be transmitted. Voice frequency signals, if we are speaking about, it is nothing but control signal or tone signal. So generally we try to avoid control signals being transmitted when speech signals are there available in our system or while the conversation is in progress. So in order to provide this, or in order to avoid this interfering, or in order to avoid signal imitation, so two signaling methods have been employed. So we make use of two signaling methods basically. So the first signaling method is tone on idle signaling. Tone on idle signaling. We know when there is no conversation, the entire system or the state will be in idle state. So whenever we observe idle, then only we will transmit tone signal or control signal, and we call such signaling method as tone on idle signaling. Similarly, we have another type, that is pulse signaling. Let us understand what is tone on idle signaling and what is pulse signaling is about. So with respect to tone on idle signaling, this was used in North America, and the basic principle behind tone on idle signaling is an idle 4-wire circuit is going to transmit tone continuously in both directions, and this continuous tone signal will be switched off in one direction by the forward sees signal. So once we know what is forward sees signal is also called as call request signal. Once the end user goes off hook, once he takes his handset up, it is nothing but off hook. Once the off hook is produced on one direction, previously we used to have tone continuously between two sides in both the direction, between two exchanges. Between two exchanges in both the direction through this 4-wire circuit, we used to have continuous tone signal being transferred in both direction, in this direction as well as in this opposite direction, with the help of this frequency generator. That is what a tone signal is, or control signal will be continuously transferred in both the directions when the system is in idle state. That means right now there is no call or there is no speech signal coming into this exchange or switching system, and now suddenly when there is C signal, or once the customer goes off hook, call request signal will be transferred to exchange, and once the exchange detects this call request signal, whatever the signal that was produced before, this tone signal will be turned off. Previously the tone signal used to go in this direction, this tone signal will be removed, or the control signal will be removed, and we will allow only speech signal to go in the forward direction. On the other hand, if this customer once he observe ringtone, this customer will answer the call by taking or by going off hook. Once he goes off hook, the answer signal must be transferred to calling customer. So once the answer signal need to be transferred, then also in order to transfer that answer signal, we will switch off this control signal in the backward direction. So in the other by the backward answer. So generally backward answer signal must be sent to the called party. So in such case, the control signal will be turned off. So please note, previously before the call is arriving the system, there exists a continuous control signal being sent in the both the direction. Control signal will be sent in the both the direction. Once the call request is coming in, the control signal will be turned off. Similarly, once he answers, in order to send backward answer signal, so this control signal will be turned off. Finally, after conversation is complete, clear signal will be produced. Once any of the end user goes on hook, clear signal will be produced. So this clear signal again will turns on the control signal. So this will switch on the signaling tone or control signal again after any end user goes on hook. So that is what tone on idle signaling is about. That is what tone on idle signaling is about. In case of pulse signaling system, so what we do is the call request signal, that is C signal, answer signal, as well as clear signals, that is forward clear signals, are all sent by tone pulses. So what we do is we will send some tone pulses or control pulses, control signal pulses, with duration typically between 50 millisecond and 700 millisecond. So generally we make use of pulses in order to send pulse signaling inside our pulse signaling system for three different types of signal. One for call request signal, for answer signal, as well as for clear signal. But the thing is, the pulse tone is, we know the pulse will go on and then off. So this pulse duration is made typically larger, generally between 50 millisecond and up to 700 millisecond. So generally the speech, we don't observe any speech going high for longer duration. So generally the amplitude will vary in our speech signal, we know that. Whereas in pulse signaling we make use of pulse and their duration is made 50 millisecond to 700 millisecond. And with respect to clear signals, generally long duration pulses are preferred. So we know clear signal is used in order to disconnect the call, and this disconnection should not happen when speech is in progress or when conversation is in progress. So that's why what we do is, generally for transferring clear signal we make use of a pulse for longer and longer duration. If there exists a pulse for longer duration, in such case the call will be terminated. So that's why, that is what pulse signaling system is about. So generally the clear signals are of long duration in order to minimize the chance of connection being released in error. Because if this clear signal goes for smaller duration, then the call will be terminated easily and that results in error. So that is what pulse signaling system is. Generally these three different types of signals are transferred in the form of pulses, and the pulse duration may vary from 50 millisecond to 700 millisecond, and generally larger pulse duration is used for sending clear signals. Thank you.